Let us go ahead take a look at an example of an isobaric problem where both the piston area and the piston's mass are given. A piston cylinder device contains R134A at 0.85 kilogram and minus 10 degrees C. The piston has a mass of 12 kilogram with a diameter at 25 centimeter. The piston is free to move. The local atmospheric pressure is 88 kilopascal. Heat is transferred to R134A until the final pressure reaches 15 degrees C. We want to determine the final pressure, changes in volume, and changes in enthalpy. We want to follow the 4-step problem-solving procedure specified in class. Identify system, process, substance, fill the property tables, determine work, and apply the corresponding first law. It is clear from the problem statement that this is a closed system problem. The substance is R134A. Since this is a piston cylinder device, the weight of the piston, the area of the piston, and the external pressure will all remain the same in this particular case. The process is isobaric, which means that the pressure will remain constant throughout the problem. The next step, specify that we need to find all of the missing properties in the table, and this will require us to have two intensive properties for each given state. From the problem statement, the initial and final temperatures are both given. Mass is also given. Since the system is closed, the mass will stay the same. We are given the mass of the piston, the local atmospheric pressure, and the piston's cross-sectional area. Let's try to draw a free body diagram to see if we can find the area inside the piston cylinder device. Externally, we have a pressure distribution apply, and the corresponding force is equal to atmospheric pressure times the area. Also going downward is the weight of the piston, which is equal to the mass of the piston times G. And inside the piston, we have a pressure distribution, which we're just going to call P1 multiplied by A. If I simply do a very quick force balance, you can see that P1A will equal to atmospheric pressure times A plus the mass of the piston times G, which is the weight. Area is defined as the area of the piston. Since diameter is given, therefore area is equal to pi times d squared divided by 4. Let's now divide area by both sides. We can obtain the relationship to find the pressure for state 1, which is here. And since the process for the problem is isobaric, pressure will stay the same. So that means pressure 2 and pressure 1 will be the same. Let's now go ahead and plug in the numbers from what's given in the problem. Then you'll see that pressure 2 and 1 are both the same at 90.4 kilopascal. We now have two intensive properties per each state. We are now ready to find the rest of the properties. Since there are now two intensive properties for both states, let's proceed to find the rest of the properties for state 1 first. Let's first find out what phase that is. Go to the saturation temperature table. Through these numbers, we can see that my phase is superheated vapor. We then go to the superheated vapor, find out what my values are. Since pressure 90.4 kilopascal is closest to 0.1 megapascal, we're going to use that number as an approximation. So my enthalpy is at about 245 kilojoule per kilogram, and my specific volume is at 0.207. Follow the same process. We will find that state 2 is also a superheated vapor. Go to the superheated table, 15 degrees, using pressure at 0.1 megapascal as approximation. We can find all of the rest of the properties in the table. Now we can specify what our final answers are. Final pressure. As you can read from the table, my final pressure is 90.4 kilopascal. To find the change in volume, I take volume 2 minus volume 1, 0.196 minus 0.176, which turns out to be 0.02 meter cube. Change in enthalpy is simply 266 minus 245, which is equal to 21 kilojoule per kilogram.